On YouTube. Testing on YouTube. Testing on YouTube. All right, I think YouTube is working. How's it going, Ed? How's it going, the Big Fortuno and Beck Pro? All right. We'll just wait a little bit, and then we will be live on X, and then we'll get started. Question from Cigar. What's the time in your region? I live in Austin, which is in the middle of the U.S., which uses the Central Time. And for me right now, it's about 10 a.m. Beck Pro, why don't you do Kaggle? I do. I have a couple streams where I was doing Kaggle competitions, but the live coding streams don't really get as much traction as these paper streams, so now the streams have kind of just become paper streams only. Question from Meme Poppers. Did you get access to SD3? No, I did not. So I'm still on the wait list, like the rest of the population, I suppose. How's it going, Tim Anderson? How's it going, 2ARX? Beck Pro, what is my tier? I don't even know if I have a tier. I think I've done like one Kaggle competition. I was probably trash, so. All right, I think we're live on X. Yeah, we're going to be live on X. All right, let me make sure it works. Okay. Let me blast this horn and then we'll get started. All right. Let me spit out this gum, actually. Welcome, everybody, to another Hoopo stream. Today, we're going to be looking at Stable Diffusion 3. This is the third and most recent release of Stable Diffusion, which is a generative image model. This is a model created by Stability AI, which is a startup that creates open source models, mostly really known for their image models. And this is the latest one. And this is a big paper. So after kind of reading through this morning, I've come to the conclusion that this might actually be the greatest diffusion model paper I've ever read. And let me kind of clarify what I mean there. So most papers that you read come from an academic kind of background. And what that means is that usually they're the result of maybe one or two people doing the work, usually students, maybe an advisor or two. And usually within a quarter or two of work, they get some result. The paper usually has maybe one kind of cool thing in it, and that's about it. This is the paper that is very clearly the result of a much larger team. And as we're going to go through the paper, this is probably the most comprehensive collection and summary of just diffusion models in general. They have every single different type of training flow here. They have architectures, different architectures. They sweep over a very large model parameter space. They talk about data. They talk about everything in here. It's 28 pages, absolutely jam-packed with all the information you could want. So if you really only needed to or wanted to read one diffusion paper, this would be the paper you should read, because I think it's just such a great summary of where we're at and all the techniques that got us there. And I guess as the cherry on top, this is currently the state-of-the-art image model, which I know is a big claim. And image generation is kind of at the top of the S-curve. So I've shown this before. This is a S-curve, which is generally the way that technology works. So when new technology gets introduced down here, you go through this phase where growth is very quick and the difference between successive versions and generations of that technology is big, right? So the difference between the early versions of Midjourney and Stable Diffusion 1, Stable Diffusion 1.5, right? Like the differences between those were quite big, but we're kind of getting to this top part of the curve where even though this is state-of-the-art and the way that they claim state-of-the-art using human evaluations, I think is a very robust way to claim state-of-the-art. So I don't think they're out of line by claiming that this is state-of-the-art. I just think that the difference between this one and maybe DALL-E 3 and some of the other ones is starting to become vanishingly small. So state-of-the-art doesn't necessarily mean much anymore. So just to kind of start off with some interesting images here, we got hashtag SD3 for Stable Diffusion 3 on Twitter, and here you can see a bunch of different images that the community has been generating. And I don't know about you guys, but this is pretty much we're at the top of the S curve here. This is almost indistinguishable from reality. You have everything from kind of like fantasy anime styles, cinematic styles. Like look at this. This is like Game of Thrones, Lord of the Rings quality. Like it's really, really high quality. I don't really see how you could possibly make this any better, right? It's not even my final form. I don't know how you could make this better, but that's where we're at. So this paper is going to explain all the different tricks. And this is, I kind of want to take a moment here to say that I really, really appreciate Stability AI. Nobody else is really doing this. All the other companies, whether it's Midjourney or OpenAI, they don't publish anything. They don't tell you what they're doing. They hide all their secrets behind the corporate veil. And I really, really appreciate that Stability AI publishes papers like this where they tell you everything, every single detail, every single thing that everyone on their team worked on is represented here. And it's just such a great quality paper. And I'm just so happy that they do this that I got to give them their props. Okay. All right. So let's get started with the abstract here. Actually, maybe hello Majetti, hello Meme Poppers, Droom, Tim, and everybody else. Diffusion models create data from noise by inverting the forward path of data toward noise and have emerged as a powerful generative modeling technique for high-dimensional perceptual data such as images and video. So what does that mean in English? It means this. This is what diffusion models do. They basically go from a pure noise distribution. So this right here, this is what noise looks like in pixel space. And this is what your data distribution or the target distribution or what you're trying to get, which is an image or the distribution of all images in pixel space. That's what you want, right? And diffusion models basically take you from noise to data. Rectified flow is a recent generative model formulation that connects data and noise in a straight line. So we're going to understand what that is a little bit later once we go into that. But for now, rectified flow is going to be the specific type of flow that they use in this paper that is better than all the other ones. We improve existing noise sampling techniques for training rectified flow models by biasing them towards perceptually relevant scales. Again, this is going to be kind of hard to explain in the abstract, but we'll go into it. There's a lot of math in this paper, so hopefully you come out of this with a pretty high-level understanding of what's going on. Additionally, we present a novel transformer-based architecture for text-to-image generation that uses separate weights for the two modalities. So not only are they going to ablate and then figure out what the best type of flow for diffusion models is, which is going to end up being rectified flow, but they're also going to introduce a new model architecture. This is what is on the background of the thumbnail. It's the model architecture for this. It's called the MMDIT, which I think stands for Multimodal Diffusion Transformer. So DIT, the diffusion transformer, is what we think is behind Sora, right? The Sora model and the Lumiere model. Sora is the video generation model from OpenAI. Lumiere is the video generation model from Google. And both of those, they're secretive, so we don't really exactly know, but based on the pedigree of the researchers that are working there. For example, at OpenAI, the guy who worked on Sora, called Peebles, Bill Peebles, this guy created the DIT architecture, so we can kind of assume that the architecture used for Sora is a DIT. So the MMDIT is like a little variant that they're going to do specifically for this paper that works better than all the other ones. And finally, of course, this paper, they're going to go and show using various quantitative metrics and these human evaluations. Human evaluations are when you basically have people looking at two different pictures, except they don't know which one is which, right? They don't know which one was generated by DALL-E 3 and which one was generated by Stable Diffusion. Pretty much the only thing they get is just the two pictures, and then they have to answer these types of questions here, such as, which image looks more representative to the text shown above and faithfully follows it? Or, given the prompt, which image is of higher quality and aesthetically more pleasing? Or, which image more accurately shows and displays the text specified in the above description? More accurate spelling is preferred, ignore other aspects, blah, blah, blah. So they get people to sit there and just pick A, B, A or B, B or A or B, and they just do this. I don't exactly know who they're picking. You know, at some point we're going to have to start maybe asking people where your human evaluators come from. I could imagine a situation where you can bias the human evaluators such that it benefits you. But for now, I feel like human evaluations, assuming kind of good faith from these companies, is the gold standard way of determining the quality of these image generation models. So if they say they're outperforming state-of-the-art models, which include DALL-E 3 and all the other competitors, such as Midjourney, then I'm perfectly comfortable with that. And because Stability AI is awesome, the data, the code, and the model weights will be made publicly available. I think it's still not 100% available. I think you got to get on a wait list. You probably have to email something to someone. You probably have to sign some weird user license agreement or whatever the fuck is going on. But eventually, I do think that they will make all of this public. So let's get started. I don't speak Russian. I'm sorry, the Big 4-2 know. All right, so into the introduction section here. Have you seen a Huawei model with a similar architecture? Not off the top of my head, but I bet you that someone at Huawei is probably doing some kind of diffusion transformer. I don't really know. Maybe I even read one of those papers. I don't really remember too many details, to be honest. I have a pretty bad memory, which is a little bit weird, but I don't know, if you post the link, maybe people will check it out. Diffusion models create data from noise, and that can be used to generate new data points that are not present in the training data, but follow the distribution of the training data. So once you have this diffusion model, which is basically a way of going from the noise distribution to the data distribution, then you can go from any random noise to some point that's going to exist in the data distribution, but it doesn't necessarily need to be a point that you actually had during your training process, right? During your training process, you're going to be training this diffusion model with a huge amount of data, and that huge amount of data is composed of individual images that are captioned, so an image with a specific piece of text, and that represents one sample from this distribution. And really what you want is the distribution, and you want to be able to sample from that distribution and get images that basically don't exist, but you're making them exist and they make sense. This generative modeling technique has proven very effective for modeling high-dimensional perceptual data, such as images. The high dimensionality here comes from the fact that any image, right, is height by width by channels. So there's a lot of little numbers, lots of dimensions in pixel space. Okay, specifying the forward path leads to efficient training. It also raises the question of which path to choose. While curved paths require many integration steps to simulate the process, a straight path could be simulated with a single step and is less prone to error accumulation. Since each step corresponds to an evaluation of the neural network, this has a direct impact on the sampling speed. Okay, so I think it's time to start to talk about what exactly is going on here. So each time you basically move from here to here to here to here, you're performing one inference step on your neural net, which means you're basically running your neural net once on your GPU, right? So here, this would represent 1, 2, 3 steps. And usually there's way more steps than that. So here, for example, you go from noise to this cat, and you can see that you basically take 1, 2, 3, 4, 5, 6 steps, right? So that would be 6 steps. So one thing that they mention here is this idea of curved paths versus straight paths. So what do they mean by straight paths versus curved paths? So the thing to realize here is that this picture is a little bit misleading in that it feels like you go from straight noise and then the noise becomes the cat, but if you were to imagine what the path of this was inside the high dimensional image space, you would think it's just kind of a straight line, right? It's going from here to the final one, but that's not really the way it looks, right? What's actually happening is the path is a little bit more curved, right? It's a little weird. So I feel like this picture kind of demonstrates it more clearly. Here you have maybe the beginning, right? This is the noisy image. And this is a kind of two-dimensional representation of a much higher dimensional space, so take it with a grain of salt. But you can see here how here you have one step. So imagine each of these lines here as basically being individual steps, right? So this is what they mean by a curved path. So most of the time when you're using diffusion models, you're not taking kind of the straight path from the noise to the actual image that you ultimately want. You're taking this kind of weird curvy path, right? And the idea of this rectified flow is that you kind of want to just take one step, right? Because if you can take one step, you can get rid of all this extra computation that you're doing by taking multiple steps, because every single step is going to be one inference, which is going to be more time spent waiting on your GPU to generate it. So if you can do it in one step, that would be a hell of a lot better. And maybe to get a better idea of what multiple steps means instead of a straight path, here you can see how it doesn't go straight from here to here. It kind of ends up in other places. So you see how this cat has orange fur. So if you were to actually think about the latent space where this lives, this high dimensional latent space, it's moving a little bit in the orange direction before it finally goes back into the gray direction, right? So it took like almost like a curve in terms of the path in this kind of like semantic space of the cat is orange, okay, now the cat is gray, right? So like, why didn't it just start off with the cat being gray? So if it generated from the beginning with the cat being gray, that would be kind of a straight path because that's where it was going anyways. But the fact that it went into like this dark brown and then gray and then white and then orange and then white and then gray, right? You can imagine that as kind of like a curvy path. So this rectified flow is all about getting rid of that curve and just going to that final point as in one step, right? We changed this, introducing a reweighting of the noise scales in rectified flow. What else? Learnable streams for both image and text tokens. I think we'll explain most of these once we get there. This paper is very information dense, so I'm trying to show it to you guys in a specific order so that it makes the most sense. And then, of course, the largest models outperform state-of-the-art. SDXL, which is the previous version of Stable Diffusion, PixArt Alpha, DALL-E 3, Midjourney, and so on. Okay, I think we'll skip these right now because we're going to kind of go into them in detail. Rant from Timothy. Yan LeCun on Lex said models can't predict missing patches in image, but isn't that in painting, Stable Diffusion, etc.? Yeah, I think, Timothy, I think Yan LeCun wasn't saying that you literally can't do that because he's literally trained models that do that. There's all kinds of like masked image type papers that Yan LeCun has released over the decades. So he's more kind of trying to talk about the kind of at a higher level where he's saying like at a fundamental level of reality, you can't actually know what's in that missing mask, right? You're kind of like, you have some distribution and then you're kind of like filling in based on what you know, and the model's kind of getting better and better at filling it in, but there's the actual true fundamental reality of like what's there is not actually what the model's putting out. It's outputting kind of almost like the statistical average of what it's seen. So I don't think Yan LeCun was saying that you literally can't do masked image prediction, because there's plenty of papers with his name on it that do exactly that. I think he's more trying to talk at like a higher conceptual level. Okay. Yeah. Okay. So let's get into the math here. So we're going to go straight into this. We consider generative models that define a mapping between samples x1 from a noise distribution to samples x0 from a data distribution. Okay, so now rather than talking about images and noise, we're going to talk about a distribution of noise. So this is this, and then a distribution of what they call here data distribution. The data distribution is this, right? So one way to think about it is that your training data set, if it's 1 million images, there's some distribution from which those 1 million images are sampled from, right? So you can think of it, if you had a magic data distribution generator and you sampled it 1 million times, you would get your training data set of 1 million images. So whenever people want to get mathy, they talk about this idea of a data distribution, but really whenever you see this data distribution P0, just think of it as images. And whenever you see this noise distribution P1, just think of it as noise. So your X0 is going to be images sampled from this data distribution, and then X1 is going to be coming from that noise distribution. Okay, so now they're going to introduce this ordinary differential equation here, dy t, and you see this little dt here, you can bring that over, and then you have dy t dt, so the derivative of y of t with respect to t, right? The time derivative of y is equal to this v of theta yt. So basically the velocity, which is the derivative of position, right? And then acceleration is the derivative of velocity. So all they're saying here is you have this dy dt equals v of theta, where this theta here is the weights of a neural net. So a neural network is a function approximator. A neural network basically approximates some function, any function, right? And the fact that they can approximate any function is why neural networks work so well. But that neural network has some weights or parameters, and here the velocity v is the function that you're trying to approximate with a neural network, and the weights of the neural network, we're going to call them theta. Okay, so this velocity here, a more efficient alternative is to directly regress a vector field, which generates a probability path between P0 and P1. So a vector field, whenever you see vector field, this is kind of what you should be thinking of. So this is a vector field in two-dimensional space. The formal definition of a field is a function that you can evaluate at any point in space, right? So whenever you say a gravitational field, what does that mean? It means that at any point in 3D space, you can say, okay, what's the gravity here? And there's a value for that. What's the gravity here? There's a value for that. What's the gravity here? There's a value for that, right? So a vector field is just kind of a field where you can choose any random point, and there's going to be an associated vector with that. And here, the vector field of this velocity, right, what you can think of is that it's basically the vector field of this, right? So somewhere, again, it's kind of hard to like imagine these things because this is all being done in a very high dimensional space, but all the pictures that I'm showing you are in two-dimensional spaces. So this is a two-dimensional vector field. This is kind of like a two-dimensional representation of moving through from the noise distribution to the image distribution. So just imagine kind of like a two-dimensional vector field here, where at any point you can get the velocity, and that velocity will effectively tell you the direction that you need to move in order to flow from the noise into the data distribution, right? So basically overlap this with this, and that's what they're trying to describe here, right? Where ultimately what a diffusion model is doing is it's saying, okay, if you give me a sample from your noise distribution, which is going to be some point in this 2D space, you can now evaluate this diffusion model and say, okay, well, what's the vector field pointing at? It's pointing at over here. Okay, let me move over here. Okay, now what's the vector field pointing at? Oh, it's pointing over there. Okay, let me move over there. And what's the vector field pointing at? Okay, it's pointing over here. Let me move over there, right? So you're basically constantly evaluating this vector field, and the vector field will take you from a point which represents noise to a point which represents a sample from your data distribution or an image. So that's a very fancy way of kind of describing formally what you're doing when you're kind of doing this image generation process with a diffusion model. Okay. To construct this vector field, we define a forward process corresponding to a probability path between P0 and P1, right? Where P0 is the data distribution, and then P1 is this N01, which represents basically a Gaussian centered on 0, which represents noise, right? So this P1, this probability path PT between P0 and P1 is just this, right? This is P0, and then P1 would be here, right? And it's a little bit confusing because it's the opposite. Whenever you're training, you're starting from the image and then you're adding noise. Whenever you're doing the inference, you do it the opposite way. But whenever you're training, you go from the image, P0, to pure noise, P1, right? So you can write that as this little equation here, ATX naught plus BT epsilon here, right? Epsilon is pure noise. So at time 1, A1 equals 0, which means if you plug in 0 here, this will be 0, and you'll just get 1 times the noise. So at time equals 1, which is the very end, is just pure noise, right? So that's what I get when I plug in this into here. Let me make sure my face is not in the way. Okay. And again, at time step, at time step 1, it's pure noise. At time step 0, if I plug in A0, 1 here, and I plug in B0 equals 0 here, I get X naught, which is just the image. So you're just going from image, X naught, to noise, epsilon. Okay. The marginals are consistent with the data and noise distribution. The marginals is basically, comes from in statistics, this idea that a lot of distributions were in these tables, and then in this tables, you would basically look at the margins of the table and add it all up, and it's basically the distributions at both ends. So in this case, the data distribution, the noise distribution. So that's what they're saying here, is that if you plug in these values here, the marginals end up either giving you the data distribution or the noise distribution. Okay, so they're going to introduce these two new things here. They're going to introduce psi of t and u of t. So u of t, remember, is this vector field. So psi of t here, you see psi of t is conditional on epsilon, right? So it's a function. It's a function that takes in a thing, and it's conditioned on this thing here. So this epsilon is what it's conditioned on. This one's also conditioned on that. So psi is basically this function up here, ATX naught plus BT epsilon, ATX naught plus BT epsilon. See that? And then u of t, which is this conditional vector field. So why is it a conditional vector field? It's because it's conditioned on this noise here, right? So if it was just ut of z, it would just be a vector field. But it's ut and then this pipe symbol epsilon, which means a conditional vector field, right? So now you're conditioning it based on the noise. You could, I think the easiest way to understand this is it's almost like in a Python function. You have your arguments and your keyword arguments, right? But you can envision it as a function that just takes z versus a function that takes that z and another extra parameter, epsilon, which represents the noise. And here, the ut z condition on e, or the conditional vector field ut, you can see here how it's the inverse of this psi, so the inverse of this thing here, and then this little tilde here means derivative, right? So basically what they're saying is that u of t, this conditional vector field, is the first derivative of this here, right? So that makes sense, right? They were just literally saying up here that you could think of this vector field as kind of the velocity, where the velocity is telling you kind of the slope or the direction that you're moving in this space as you're going from the noise to the image, or the image to the noise. Right, so that's all they're saying here, is that this conditional vector field is basically the time derivative of this equation here. Okay. Marginal vector field generates the marginal probability path using the conditional vector field while regressing UT with the flow matching objective. So, okay, now we're talking about regressing UT. So when we say regressing UT, what we're saying is we're trying to get UT, right? So when we regress something, we want to get it. We want to get the actual value for that, right? And in order to train a neural network to regress something for us, we're going to need a loss, right? So this little LFM here, this is the loss function that you would use to get the UT, or the vector field, and that's known as the flow matching objective. So you can see here, it's pretty simple. We just have the UTZ, which is what we want. And then we have this V theta ZT, which is what we're getting, right? This is our little neural net. So we're plugging in this Z and this T into our little neural net. It's giving us a value. And then this is the one that we actually want. And then we're just doing a little L2 loss here. So this is basically just the difference squared, and that's known as the flow matching objective, right? The problem with that is that it's intractable. So why is it intractable? It's because of this UTZ, this PTZ conditioned on E over PT. We don't know what this is, right? And because we don't know what that is, or this UTZ right here, right, we're going to have to do conditional flow matching. So now you see how this equation 8 compared to equation 7, it's basically the same exact thing, right? LFM, except now it's LCFM, conditional flow matching. And the only thing we've done is we've replaced this UTZ with this UTZ pipe E, or epsilon, where this is now the conditional vector field compared to this not unconditioned, just normal vector field here. Right, and this is the expected value of that, the same thing, it's an L2. Here you have the conditional probability path, and then the noise distribution. Okay, so now that we have this conditional flow matching objective, that's an equivalent yet tractable objective. So we've now moved from something that we want to do, which is getting this U of t, but we can't really calculate this, to now we can calculate something slightly different, right, with this conditional vector field, but we can actually calculate that, so that's what we're going to use. Okay, and now what they're going to do is they're going to insert these equations that they had up here, and they're going to basically put them into this equation here, do a bunch of math, and eventually get to the loss that they want to use, this one here. So LCFM, and then this is the full formulation. So what did they kind of do here? They introduced, for example, this signal-to-noise ratio, lambda t. So this signal-to-noise ratio, lambda t, what are the two parts of that? Well, if you notice that, you see this a of t squared here and this b of t. What are those? Well, we scroll back up here. A of t is the thing that multiplies x naught, right, which is our data, our image, which is our signal, right? So that's what we want. So this a of t is like the thing that we actually want. And then this b of t is multiplying this little epsilon, which is the noise. So it kind of makes sense that the signal-to-noise ratio is this a of t over this b of t, right? Because it's basically like the thing that multiplies the image, and then the thing which is our signal, and then the thing that multiplies the noise. Okay. So they plug that in. They do a bunch of little math here. It's still the same equation, right? It's still the same equation. They're just kind of substituting these things in. And you can see then they do one little flip here, right? And they say a noise prediction objective. Okay, so they flipped it. They kind of like, they pulled a little 3-cup or 3-card Monty, right? And you have to notice it because it's a little quick. But you see how they went from this to now this, right? So previously, up until now, they were basically matching the flow or matching the vector field, right? They were trying to match this velocity. So the neural network is literally outputting the velocity, right? That's what this V of phi is doing here. V of theta ZT. But you see now how they've switched it, and now it's epsilon theta ZT. So it's no longer, your neural net is no longer outputting these little velocity vectors, right, which will tell you where to move. Sorry. It's no longer outputting these. What it's outputting is the noise, right? So now it's outputting the noise, which is much easier to calculate, right? Because before you were trying to say, okay, well, what's the difference between the velocity vector that I calculated and the velocity vector that my neural net gives me, and the velocity vector, the true velocity vector, the thing I don't actually really know? Now I've kind of substituted in a bunch of different things here, and now this is much easier to calculate, right? Now it's just, okay, what is the noise that my neural net is predicting, and then what is the noise that is actually there? And that you can know because whenever you're doing this, you added the noise yourself, right? So you know exactly what the noise is because when you're training, you're adding the noise yourself. So you know what this epsilon here is. And because you know what that epsilon here is, this noise prediction objective makes it much easier to do than this flow matching objective up here. Okay. Note that the optimum of the above objective does not change when introducing a time-dependent weighting. Thus, various weighted loss functions that provide a signal towards the desired solution but might affect the optimization trajectory. Okay, so now what they're going to do is they're going to take this equation here, this little loss function. They're going to rewrite it. So you see now they've rewritten it. It's basically the same thing, but they've rewritten it such that you have this term here, this WT. WT in this case is -1/2 lambda t tilde b squared t. And the reason they've written it in this form here is because they're going to show you that all the other diffusion models and diffusion papers that you've read are all just different variants of that. Okay. So what do I mean? What I mean is that here in section 3, so section 3 flow trajectories, they're going to introduce, or they're going to show rectified flow, EDM, cosine, and then LDM linear. And these are different solutions or different variants to this ultimately loss function that you're solving here, right? So for example, EDM comes from this Karas 2022 paper. Cosine comes from this Nickel and Dhariwal 2021 paper. LDM linear comes from this LDM Rombach et al. 2022 paper, right? So this is kind of what I mean by this paper is such a great diffusion paper because it summarizes all the other papers and all the different techniques that they've done. And the one that's going to end up working best, I'm going to kind of cut to the chase here, but in this paper, they're going to try all of them. So they're going to say, okay, well, let's see all the different ways that people did this out there in the world. We're going to try all of them, compare them head to head, and then we'll tell you which one works the best, right? So after this paper is published, hopefully no one ever has to do this EDM or this cosine or this linear anymore because it turns out that this one is the best one, rectified flow. So rectified flow defines the forward process as a straight path between the data distribution and the standard normal distribution. So here's that straight path right here. Right, so here's your boom, boom, boom. This is not a straight path, right? This is a series of steps. Rectified flow is going to be this. It's going to be one boom, one straight path straight from the noise to the data. Right? And you can see it's actually very simple, right? Here, z of t, 1 minus t plus t, where if you compare that to this equation, right, you're literally just saying that there's a straight line, t over 1 minus t, that goes from x naught, or from the noise to the data, or from the data to the noise, right? So it's actually the simplest possible form for this, right? Because rectified flow, compared to some of these other ones are way more complicated, right? Like, look at this shit. You know, the quantile function of the normal distribution. This cosine one has this like multiple cosine sine pieces. Like, these are more complicated, and somehow we lucked out as humanity, and rectified flow is actually the best variant of a flow trajectory to use as a loss for these diffusion models. Okay. I'm going to pause there for a second. Does that mostly make sense to you guys? Okay. So they've showed us what you're fundamentally doing with a diffusion model. They then show what all the other diffusion papers are doing, and then say this one ends up being the best. We're going to show you that later. And then they also do the same thing here. So there's also what's called the sampler. So the sampler is how you actually get the noise, right? So remember when I was like, oh, and you get the noise because you're actually adding the noise yourself in training. So how do you actually get that noise? This is how you do it. And there's a bunch of different ways to do that. So actually, no, never mind. This is where in the trajectory you're sampling your points that you're then going to use to train. The resulting velocity prediction target is more difficult for t in the middle of 0, 1, since for t equals 0, the optimal prediction is the mean of p1, and for t equals 1, the optimal prediction is the mean of p0. So what they're saying here is that here at the beginning, right, you're closer to the noise distribution, versus here at the end, you're closer to this data distribution. So whenever you're training this, right, you're going to be training this diffusion model with samples from your data distribution. So you're going to sample from your data distribution, which is going to be a bunch of images. And then you're going to have to decide the value for this t. So you're going to pick a value for t, right, where t is either 1 here or 0 here, right? So what value of t do you pick? Do you just pick based on a uniform distribution, which is kind of what they're saying here? So in general, changing the distribution of t from the commonly used uniform distribution ut. So what they're saying is that most diffusion papers, they basically just pick a random t that's in between 0 and 1. So they're going to train, and whenever they're training, they're going to pick a random image, and then they're going to pick a random t from either pure noise all the way to here, which is t equals 0, and then t equals 1. They're going to pick a random time step t, and then that's what they're going to be training. That's the little step that they're going to be pushing a gradient on based on this rectified flow. But what they realize is that maybe that's not correct, right? Maybe we should be sampling t's based on where they are, right? We don't really want too many t's that are too close to here or too close to here. We really want t's that are right here, because that's where the task has kind of the most difficulty and most kind of juice, right? It's like you really like going from this one to this one. That is really where your diffusion model is going to have to work hard to understand the actual distribution and exactly what is going on in this image, right? Going from here to here or from here to here, there's not as much juice in that. So in a similar way, they're going to say, okay, we're going to catalog. Here are all the different ways that people sample from that, right? So you have logit normal sampling, mode sampling with heavy tails, and you have coast map, right? So these are different types of sampling for determining the value of that t or the distribution of those t's that you're going to have when you're training this. And as before, I'm going to kind of cut to the chase here, and the one that's going to end up working better is this logit normal sampling. So one option for distributed is that puts more weight on intermediate steps is the logit normal distribution. The logit normal distribution is parameterized by this location parameter m and the scale parameter s. The scale parameter controls how wide the distribution is, and the location parameter enables us to bias that's time step. So down here in the appendices, you kind of get a little bit more example of what exactly this looks like, right? So the logit normal distribution is here on the right. So here on the right, you see on this x-axis, this is the variable t, and you see here at t equals 0, this would be the image distribution. T equals 0 is going to be this, right, here. T equals 0, or t equals 0, and then t equals 1 is going to be here, right? So you see how this is not a uniform distribution at all, right? Like this orange one here is a uniform distribution. You see how there's uniform probability of picking a value of t 0.01, picking a value of t 0.05, picking a value of t 0.9, right? Like no matter where you're kind of uniformly sampling along that t. But this logit normal distribution, which is just some arbitrary choice, right, has this kind of more central kind of like mass bump here, right? And what that means is that most of the time, when you're choosing a value of t to train for that specific data point, you're going to most often pick t's that are right in the middle, right? And that, according to their intuition, is going to allow you to get better diffusion model, because those intermediate steps are kind of more important for really learning how to remove noise or predict noise, because you're kind of in between the noise and the data distribution there. So does that kind of make sense for you guys? Maybe? I'm kind of skipping over. So here's my reasoning. So for both of these sections, right, in this flow trajectory section and then in this tailored SNR samplers section, they describe the hyperparameter space. So whenever you're training a neural net, you don't actually know what the value for a lot of different variables should be, right? So you don't know whether you should be using logit normal sampling or coast map. You don't know whether you should be using LDM linear flow or whether you should be using rectified flow, right? You don't know that beforehand. You have to perform an experiment, and then you perform that experiment, and then you see which one works better, right? So the beautiful thing about this paper is that they say, okay, well, here are all the different ones that people have tried in all the other diffusion papers, and we're going to try all of them and every single combination of all of them, right? So we're going to try rectified flow with coast map. We're going to try EDM with logit normal sampling. We're going to try rectified flow with logit normal sampling, and they're going to try all of these and see which one works the best. So we're going to skip a little bit to the section here where they do these experiments. We aim to understand which of these approaches for the simulation-free training in equation 1 is the most efficient. Okay, so we keep scrolling, and then here you go. For all 24 combinations of sampler settings, we repeatedly compute the variants that are Pareto optimal according to CLIP and FID scores. So they're going to basically train a net with, for example, rectified flow, so RF, and then log norm. And here's EDM, and then here's the V with cosine. So every single one of these is a different combination of the different techniques that they introduced in this beginning paper, in the beginning of this of the paper here, right? And ultimately, what they observe is that the rectified flow with this log normal sampling, where you're basically you're more often sampling in the middle of that time right? So most of the time it's like between t equals whatever it is here. Look at this. So most of the time you're kind of performing or predicting the noise somewhere in between here, 0.4 and 0.6. That's where most of your training instance examples are going to be, right? So this logit normal distribution with rectified flow. Let's go back up here. And that one seems to perform the best. So this is kind of like a weird way to measure it. But the way that they measure this is that they try all the combinations. And whenever you're training a model like this, generally you're doing this exponential moving average. EMA weights, the easiest way to think about it is it's like the average of a bunch of weights. So when you push a batch of data through a neural net, right, you're going to evaluate the output based on your loss function. Because your neural net is composed of a bunch of little differentiable parts, you can then calculate the derivative of that loss with respect to each of the individual little weights or parameters of your neural net. And then because it's all differentiable, you can backpropagate, you can basically chain rule all the way, and you're going to basically change the value of all those little parameters just a little bit, right? And you're going to do that for a bunch of different training steps. The EMA, you could think of it like if you had a bunch of GPUs and each of them were getting batches of data, you're going to kind of combine all of those together, and you're going to do kind of this average of all of those weights. So you can think of the EMA weights as kind of like the representative of the like multiple weights, because in this case, the problem, the main reason you want to use EMA here is because you don't want to be sensitive to the very last batch of data, right? If you don't have this EMA, the very last couple batches that you push through that neural net are going to have the most effect, right? So you might end up in like a weird place, and it might just be, you might end up not having a good score here because you just ended up feeding a batch of data that was a little bit weird. So they're using EMA weights to compare all of these. Once they have those EMA weights, they're going to compute the CLIP and the FID scores. We can actually scroll up here. So CLIP scores. CLIP is a model that contrastively trains language and image to basically project text and images to project into the same latent space. So the CLIP score is a way of saying, okay, how similar is this text, the embedding that I get from this text, compared to the embedding that I get from this image, right? FID is Fréchet inception distance, and I hate this metric because it uses a really old model called the inception model, but someone has been listening to my streams because they now calculate FID on CLIP features. So at least they're now using CLIP feature space as opposed to inception v3 feature space. So FID in this case is really FCD, F CLIP distance, which I think is a better variant of the FID. So +1 to that. They feed the Coco 2014 validation split. So Coco 2014 is like a data set, right? The validation split is some specific subset of that. So the split means that you're going to say, okay, here's my data set. I'm going to split it into the training, the validation, and the test. So I'm going to take Coco 14. I'm going to take specifically the validation part of that. And the validation part of that is going to be some folder with a bunch of images that each have some caption. And then I'm going to feed that caption into the language of CLIP, get an embedding from that. I'm going to feed the image into the image part and get some embedding for that, compare that, and how if they're very close, that means it's a good CLIP score. If they're very far away, it's not a good CLIP score. Same thing for FID, right? So FID is also a distance metric. So the smaller it is, the better, and the bigger it is, the worse it is. So there's a lot of terminology in here, but they run that with all the different variants, and ultimately what they discover is that the best variant is this rectified flow with this log norm time step sampling. Consistently achieves a good rank, outperforms a rectified flow with uniform time step, and thus confirms our hypothesis that intermediate time steps are more important. Among all the variants, only rectified flow formulations with modified time step sampling perform better than LDM linear used previously. We also observed that some variants perform well in some settings, but worse in others, and so on, right? And these rectified flow like pretty much dominate the field. So if you look at that, all of these top 5 out of the 24 combinations of sampler settings, the rectified flows were always at the top. If you look here, here's metrics for different variants. So again, smaller FID is better, smaller clip is better, or actually bigger clip might be better. I don't exactly know. Maybe I got that wrong. Smaller FID, these are different data sets, CC12M, ImageNet. You can see all of the best scores are all with this rectified flow and log norm. So basically what we've learned, and thank you Stability AI for performing this experiment for us, is that here's fundamentally what diffusion models are. Here's a way to write as a loss or an objective that you can basically changing this variable here. You can describe all the different types that people have been doing and all the different types of flow, and then all the different ways of sampling that time step. And we've tried every combination of those, and the one that we found works the best is this rectified flow here, which is actually the easiest one to intuitively understand, which is, like I said, pretty lucky. We got lucky that this is the easiest one to understand, ended up being the best, right? We could have ended up with this one being the best one, which would have sucked. And the log normal sampling is the best sampler, which kind of sucks, right? If it would have been uniform, that would have been better, right? Because uniform with rectified flow is like the simplest possible combination, but uniform doesn't perform as well as this log normal sampling. Okay. So that is the rectified flow part of this. Allows rectified, but even outperforms them. Okay, rectified flows are sample efficient. Rectified flows perform better than the other formulations when sampling fewer steps. So this is the number of sampling steps down here. This is the x-axis. This is basically how many. So here you would have 1, 2, 3, but you can have way more, right? So you can have 50 steps. The more steps, the better the performance usually. Here you have Frichet inception distance, right? This is a distance metric, which means the smaller the better. And here what they're showing you is that RF log norm, that particular combination right there is better than all of them. So you can see here, obviously it's worse doing it in one step. You're not going to get a better score than if you do it in 10 steps. But what you want to see here is that this green line, right, this rectified flow with the log norm sampling is better than, for example, this EPS with linear, or EDM, or V with linear, or V with cosine, and so on. All tables should have an arrow for high, low, best. They have the arrow here, so FID, lower is better. SSIM, structural similarity measure, something like that, higher is better. Peak signal to noise, higher is better. But we're going to go into, we'll go into this one after this. Okay, so now we talked about the flow and the sampling, and which of those two ended up being the best. So the best combination of those two. Now we're going to go into the model architecture. And let me take a pause here to take off my hoodie and drink a little bit of coffee, but I always get excited and then I just start sweating, you know? Like, look at this. Look at those sweat pits, dude. That's nasty. Okay. So, as I was saying at the very beginning of this stream, the reason this is the greatest diffusion paper ever written is because it represents the work of like an entire team of people, right? So there isn't a single human on the planet that could do all this work in a couple quarters, right? And most of the time you read papers, it's the work of largely one or two people. And that's why most papers, usually there's only one trick, right? There's like one little thing that they found and that's pretty much the paper. But this paper is extremely information dense because every single section is like the work of a couple different people. So this first part of the paper, right, where they find this mathematical formulation that can be used to describe all the different types of flow trajectories that people have tried and all the different types of samplers, that was probably a specific group at Stability AI that worked on that. And now this text-to-image architecture, that's probably a different group of people, right? So this paper is like, each little section represents probably a different team or at least a different person and the work that they did. So when you're looking at this and you're like, holy shit, how the fuck can one person like think of all of this? It's not one person. You know what I'm saying? This is multiple people, and this paper represents the work that this entire company did to get to this model, right? Which is why I really, really appreciate what they do, because now I get to know what everyone at Stability was doing, right? So I'm like, oh, okay, so they had some kind of more mathy people figuring this stuff out, and then here, now they had some kind of more model architecture type people figuring this stuff out. So let's see what those people figured out. Okay. So text-to-image architecture. This is the new variant of a diffusion transformer that they made. So we use pre-trained models to derive suitable representations. I don't know why I highlighted that. You have some text conditioning C. The text conditioning C is basically what you're typing into the prompt whenever you generate an image with this. And the equivalent of that is basically whenever you have your data set, you have your image and your caption. The caption is that C, right? That text. They're going to be feeding this text into pre-trained frozen text models. So you see here, the caption or the text conditioning is being fed into these three models here: clip G14, clip L14, and T5XXL. You can go down and see specifically those details here in this appendix. So clip comes from this. There's lots of different types of clip. They're using this one specifically, clip L14, open clip BG14, and then also the T5 text encoder, which is from Google. This one here, T5 V1.1 XXL. Just some giant text encoder trained by Google. Okay. Multimodal diffusion. Our architecture builds upon the diffusion transformer, which is this Peebles paper, right, which is the guy who now works at OpenAI. DIT only considers class conditional and uses a modulation mechanism to condition the network on both the time step of the diffusion process and the class label. We use the embeddings of the time step T and the sequence representation of C text. I don't think any of this is super important. Sequence consisting of embeddings. We add positional encodings and flatten the 2x2 patches of the latent pixel representation to a patch encoding. After embedding this patch encoding and adding the text conditioning to a common dimensionality, we concatenate the two sequences, a sequence of modulated attention and MLPs. Okay, this is the important part here. Two separate sets of weights for the two modalities, which is equivalent to having two independent transformers for each modality, such that both representations can work in their own space, yet take the other one into account. So what does that mean? So here in section or figure 2b, they show you the architecture of this MMDIT. And if you look at it, it kind of it feels like every other transformer, right? You have your attention mechanism right here, and then you have your multi-layer perceptron down here, right? But what is different about this is that you see how this is separated. There's a different multi-layer perceptron here and a different multi-layer perceptron here. So it's kind of like in a mixture of experts model, you have one attention block or one attention computation here, and then you pick a different MLP based on where your router puts you, right? So you're in a mixture of experts, you have probably 8 of these MLPs here. And they're doing something, it's not the same, but it's similar. What they're saying is, okay, we're gonna have one attention, and then we're gonna split the MLP. So we're gonna have a separate MLP, one for the images, and then one for the text. And we're also gonna concatenate these, right? So they're basically, what they mean here by such that both representations can work in their own space, yet take the other into account. What they're going to do is that this attention mechanism is not going to be a cross attention. So what you'll see in other transformer or in other diffusion models is that they use cross attention, right? Actually, let me pull that up. Let me do cross attention. So here's a little standard transformer, open image in new tab. So you see here, imagine this was your text information and this was your image information. So you would have, for example, here would be self-attention, where all the information of the image, which is being patchified and turned into a sequence of patches, pays attention to all the other information in the image, right? That would be self-attention for the image. Then people will do this cross-attention. In this cross-attention, right, you have your queries, keys, and values, and some of those are coming from the, or the queries are coming from this one, and then the keys and values, or I think I might have those confused, but the cross-attention, you're basically, you see how you're mishmashing that. That's not what they do here. What they're doing here is they concatenate that. So they take the image as a sequence of tokens, and then they take the text as a sequence of tokens, and they just concatenate them together. and then they do a self-attention, basically, between the concatenated image and text and the concatenated image and text. So any part of the text sequence can actually pay attention to any part of the image sequence, and any part of the image sequence can pay attention to any part of the text sequence. And that's kind of the key there, right? Is that you're not doing this cross attention where only the Q's and the K's specific to each modality are doing this attention map. You're doing the attention map between the concatenated text and the concatenated image, or the concatenated text and image and the concatenated text and image, which is kind of a clever design. And then they separate it out. So this attention is between the concatenated things, but then as soon as you're done with this attention, you separate it out and you do a separate MLP for the images and a separate MLP for the text. So that's the multimodal DIT block. Most of this other stuff is pretty standard here. So you have RMS norm. This is like basically equivalent to this norm here, right? These normalizations, layer norm, layer norm. They have to project these, I think, to get to the same dimension. That's what they're talking about here with this flattening. What else? Here's your positional embeddings. All right, so your positional embeddings are telling you where within your text you are or where in the image you are. The symmetric design is beautiful. Yeah, I think it's a very clean. It's basically, as soon as I saw this, like the way that they describe it is like, oh, it's almost like having two independent transformers, but you join the sequences of the two modalities for the attention operation. That's the way they describe it. But the way that I see it is it's almost like having a mixture of experts with two experts, and you have one expert that's the image one, and then one expert that's the text one. But I really like this idea of concatenating and then doing the attention between the concatenated image and text. I thought that was good. The negative of that is that now this is huge, right? So cross attention, it's going to be the length of the image sequence with the length of the text sequence, right? So the two sides of the square, where the area of the square is representative of kind of how much computation it takes to do that. So in any kind of attention map, right, the length of the sequence determines the computational complexity and memory complexity of that operation, right? So if you're concatenating all your image information and all your text information before you do this attention operation, it's going to be more expensive than if you're doing cross attention. So the negative to this is that it's more computationally expensive, but the benefit is that basically these representations can take each other into account. They can pay attention to each other, which is clean. And then the separation of the MLP is nice too. Okay. Did that kind of make sense? Hupo needs to get more hackerish and get some computer fans in the hacker sweatshirt. Yeah, I have some fans in this room whenever I run my GPUs. Question from Tim. Do you think diffusion models will contribute to AGI as LLMs or remain a creative human tool? I think people are already using diffusion models. I think if you want to think about AGI, diffusion models will largely be used for generating synthetic data for training the multimodal vision language model that will eventually be AGI. So AGI is eventually going to be some kind of vision language model with some kind of like planning attached to it, right? So planning, I'm thinking like some kind of chain of thought, maybe some external memory, some kind of RAG type situation where the model can basically look at different chain of thoughts, reference previous information that's been stored in some external database. So you have to basically add on the extra memory. You're going to have the base model itself, which is going to be some kind of vision language model. But then, and that's going to be roughly the architecture for AGI. But in order to train this type of system, I think you're going to have to train it on this curriculum of synthetically generated data. And the text component of that synthetically generated data will come from a language model, but the image component of that synthetically generated data will come from a diffusion model. So will AGI have a diffusion model in it? Probably not. But will AGI be trained on some data mix which includes data and images that have been generated from a diffusion model? Yes. So that would be my answer to your question. Question from Sporkamat. Can you think of a diffusion model as some kind of thinking, like iteratively improving the response? It's not really doing planning, right? So the diffusion model is basically is just moving in this space where noise represents some point in that space, and then the final image that you want represents a different point in that space. So whenever you're running your diffusion model multiple steps to get to your final image, what you're doing is you're basically moving a little bit in that space, and then you're moving a little bit in that space, and then you're moving a little bit in that space. And the diffusion model is basically telling you this vector field of like, where do you need to move to get to the actual point from the true data distribution. So this is not like planning, right? It's not, I don't really see this as like thinking. It's just kind of moving in the direction that it's been trained to have. I don't know. It's kind of hard to answer your question because there really isn't like a formal definition of what thinking and planning means, right? Like, in a sense, if you kind of blur your eyes, like, yes, there's some planning kind of happening here, right? Because like ultimately it knows where it needs to go before it takes that step, but it doesn't think about, it doesn't have like some kind of like thinking that it's doing. It's not like storing intermediate answers, and like, it's just literally, you just like plug in the variables and then out the other end comes the step, and that's it. I don't know. If you were to do it with text, so instead of pixels, text tokens. Yeah, I saw that. So I saw a diffusion model with text. I saw like let's see if I can search this on Twitter here. I saw a GIF of someone doing that, and it was pretty cool. I'm not going to be able to find it on stream, but there was a GIF that I saw of diffusion in text space, and you can see a paragraph that kind of looks like gibberish, and then you perform inference steps, and then the tokens get closer and closer to the final token, which is kind of a cool thing. I'll post it on the Discord. I think it is on the Discord, but diffusion in text space is definitely a cool idea that nobody has really explored yet, or people have explored it, but it doesn't really have the same traction as the autoregressive kind of transformers, which is what everybody's using now. Okay, let me sip this coffee. All right. So far, what have we done? So far, we've read the section on flow trajectories. We've read the section on the sampling for the time step. And now we've read the section on this new multimodal diffusion transformer architecture. And much like there's one more thing we want to look at here. So at the very end here, they say we parameterize the size of the model in terms of the model's depth D, i.e. the number of attention blocks, by setting the hidden size to 64 by D, and then the number of attention heads equal to D. So why do they do this? So what they're saying is that if you can think of this as being one block, right? So one MMDIT block, and then the output of this MMDIT block is just going to go into another MMDIT block. So here's your MMDIT block 2, and then there's going to be an MMDIT block 3, and there's going to be an MMDIT block 4, right? And they're going to go all the way to dimension D. But there's other dimensions in here, right? So, for example, this MLP has some width, right? The width of that model, right? So what is the width of this layer here? What is the number of attention heads, right? So this attention mechanism here, it's a multi-head attention, right? So there's some number of heads there as well. So there's a bunch of different numbers that you need to pick in order to fully define this model architecture. But that hyperparameter space is kind of big. So what they're going to say is they're going to say, okay, we're going to reduce that down to one number. So there's going to be one number, which we're going to call D. And if we pick a value of D equals 1, which means there's only going to be one MMDIT block, then the hidden size or the width is going to be 64 by D or 1. And the number of attention heads is going to be 1. So basically they're picking the different dimensions of this architecture based on a single number, and what that allows them to do is it allows them to kind of do these scaling comparisons in a cleaner way, right? So if we actually scroll here, here we go. So this is the scaling study. So scaling study is whenever you try different sizes of your model, so small model, medium model, big model, and you see how they compare, right? But you see how the model size isn't total number of parameters, it's this D. So a D equals 15 compared to a D equals 38. So the D equals 15 is not just 15 transformer blocks and that's it. It's 15 transformer blocks with a slightly less wide and slightly less attention heads. Versus D equals 38, not only is it more transformer blocks stacked on top of each other, but it's also wider and the number of attention heads is also bigger. So they've parameterized the model scale, all the different numbers that could change the scale of the model into just one number so that they can do these type of scaling studies and say, okay, well, really we could try something that doesn't have a lot of transformer blocks and is very wide, or we could try something that is very deep and and not very wide at all, or something that has not a lot of multi-head attentions but is very deep, right? This space can get very complicated, but rather than doing that, they're just going to say, okay, we're going to just pick one number, and that number will basically tell us what all the different dimensions of this architecture are, which means that it's easy to do these kind of scaling studies. And the result is quite obvious. The bigger you make this model, aka the bigger value you pick for this D, the better it performs. So validation loss goes down, with the biggest model having the lowest validation loss after 500,000 training steps. Training floating point operations, which is just a different way of measuring how much training has occurred. Same thing happening here, right? The bigger model is performing better, aka has the lower loss. Okay. Sam M. This is great, but we really need open video model from Stability. They do mention that. So they do kind of like casually mention that. Somewhere here in the bottom of the paper, let me go to this. Right here? No, right here? Yeah, we conduct, so buried in section 5.33, they say we conduct a preliminary scaling study of our MMDIT on videos. We add full attention over all spatiotemporal tokens after the spatial attention operation before the feed-forward layer. So this is not like super advanced. What they're going to basically do is they're going to kind of concatenate the time dimension as if it was extra batches, right? So collapsing the temporal dimension into the batch axis. So they're basically trying out video. So Sam M, they are trying to do video. It's just that I don't think they really got anywhere, so they probably didn't release it. That's my idea, is that they probably did have someone that took this model and then tried to see what it would do with videos, but it didn't probably work well enough for them to show that, right? Especially after the Sora paper came out. So I bet you what happened is that they were probably planning on releasing the video and the image, but the image was state-of-the-art, but the video wasn't, right? So rather than say, hey, here's our image and video, and the story or the narrative would have been, hey, the video's not as good as Sora, what they did instead was like, okay, well, let's not talk about the video stuff that we have. Let's only talk about the image stuff because our image stuff is state-of-the-art. So the narrative then becomes, okay, Stability AI releases another image generation model that's state-of-the-art. Huzzah, right? And then they can spend another quarter or two getting the results for the video a little bit better. But they did talk a little bit about the video here, even just like kind of for 2 paragraphs here. So they are trying to do it. It's just that they're not. Maybe they'll release a different paper for the video one in a quarter or two. The biggest model outperforms DALL-E 3. You want to know something super ironic? These cats are generated using DALL-E 3. So the thumbnail for my video where I review Stable Diffusion 3 uses AI-generated cats that are generated with DALL-E 3. So don't let Emod know, because he's going to be pissed. But if he's pissed, give me access. Dude, I'm talking about your papers. Give me access to SD3. Why am I waiting on the list like a normie? Okay. So we looked at the model architecture. We looked at this depth. The way they compare these is basically the FID, but the cool FID. So whoever at Stability decided to use FID with clip features as opposed to inception features, high five to that person. Mostly they're going to be training these on ImageNet and CC12M. CC12M, we've looked at this before. This is the CC12M dataset page on Papers with Code. So you can see here, it kind of came out in 2021. This is kind of how much usage it's been had. These are all the different papers that use CC12M. You can actually go on on Hugging Face, I guess, if you really want to download this dataset. Can you just like download this? Maybe, I don't know. Here's some similar data set, blah, blah, blah. It's basically just captioned images, right? So you have pictures and then you have a caption of that picture. But as we saw in the previous paper, the captions aren't very good. So the nature of human-generated captions that come overly focus on the image subject and usually omit details describing the background or composition of the scene. So therefore, they're going to do what everybody else does, which is augment these captions. So they're going to use an off-the-shelf, state-of-the-art vision language model, Cog VLM, which I think we actually did a stream on, to create synthetic annotations for our large-scale image dataset. So they're basically going to take all these CC12M images, and they're going to take this caption, and then they're also going to feed this through Cog VLM and get a different caption, and then they're going to combine those captions. You can be much more tricky, so it seems like they actually did a very simple version of this. They just like 50-50 original versus synthetic, but I've seen more fancy versions of this where people take the VLM caption and then use an LLM to combine it with the original caption and then use an LLM to further elaborate the caption. So you can have much more fancy caption augmentation techniques, but here the one that they use is actually quite simple. And this is the only part of the paper that I feel like is actually, I'm a little bit disappointed. They only tell you, they said that they try original captions and then a 50-50 mix of original and synthetic captions. But I would have loved to see more of an ablation here. I would have loved to see like 0-100, 50-50, 100-0, 75-25, 25-75, right? Like show me the U-shaped curve, right? Show me the fact that 99% synthetic works worse than 80% synthetic, right? I feel like they probably did that, but they just didn't tell us about it, which is a little bit disappointing. But that's really the only thing about this paper that I thought was a little bit disappointing. Overall, this paper's really good, so I don't know. Latent diffusion models, here's another little section. Latent diffusion models achieve high efficiency by operating in the latent space of a pre-trained autoencoder. So what they're saying here is that usually these diffusion models aren't in pure image space, right? They're not actually happening in pixel space. What they're happening in is latent space. So a latent space, I have here a autoencoder. This is an autoencoder that uses a convolution. This is like a very old classic autoencoder. I just picked this image because it just is easy to understand. So an image here, a 28 by 28 by 1 image. Normally, most images aren't grayscale, which is this one. Usually they're colored, so there's 28 by 28 by 3. But you can see here that as your autoencoder, as you get more close to that bottleneck, the channel dimension increases here. So you see how the image goes from being a 28 by 28 by 1 to now being a 3 by 3 by 128, right? So this is the feature or channel dimension gets much higher, and then the spatial dimension gets much smaller, right? So the bottleneck of that autoencoder is generally what the latent space in which you're performing this diffusion. So even though every single image I've showed you is in pixel space, these diffusion models aren't actually operating in pixel space. They're operating in this latent space. And what they're saying here is that fundamentally, the reconstruction quality of this autoencoder provides an upper bound on the achievable image quality. So if your autoencoder, which is this part here, the one that takes the latent and then blows it back up into an image, if that is shit, your entire generation pipeline is going to be shit, right? So like this is kind of an upper bound on how good the quality is, right? And increasing the number of latent channels D significantly boosts reconstruction performance. Unfortunately, they choose to use the same variable name for the model size, which is they use D for the model size, but they also use D for the number of latent channels here. But they're saying that as we have bigger and bigger models, right, models with increased capacity, aka bigger models, should be able to perform better for larger D, ultimately achieving higher image quality. So they're saying that the bigger you make this 128 here, right, this channel dimension here, or this feature dimension, the better the reconstruction quality of this autoencoder, and the better the quality of your entire diffusion pipeline. So if we're getting bigger and bigger GPUs each year, and bigger models are capable of using these bigger feature dimensions, then we should just be increasing this every year. And that kind of makes a ton of sense intuitively, but they're just kind of confirming that. I think they literally have a plot on it as well. Let me see. Do they? No. Okay. But they try, and obviously it makes sense. D equals 16 is the best dimensionality, the biggest one, but D equals 2 is worse than D equals 4, which is worse than D equals 8, which is worse than D equals 16. So why did they not try D equals 32? Because the GPUs just aren't big enough. But it's a promising result, because it means that next year, maybe NVIDIA makes a bigger GPU and we can try D equals 32. And then 3 years from now, NVIDIA makes an even bigger GPU and we can try D equals 128, right? And as we keep increasing the dimensionality of this latent channel dimension, we're going to get better and better autoencoders, so we're going to get better and better diffusion models. So there you go. We're just going to wait until they make bigger GPUs. What else? We're kind of bouncing all... Okay, here it is. So 4 channels versus 8 channels versus 16 channels. So this is the dimensionality of that. So this number here, this 128. So obviously 16 better than 8, better than 4 in every single metric. Scaling works, guys. Original versus 50/50. Oh, this is kind of cool. Look at that. So the synthetic captions seem to like help with color, counting, single object, 2 object. I don't exactly know what these are. I'm assuming this is like you ask it to generate 2 of a thing and it accidentally generates 1 of a thing or 3 of a thing. So like how often does it generate the wrong number of things? So obviously if you have synthetic captions, you're probably going to have your text information is going to be more precise, so that ultimately your diffusion model is going to be better at producing exactly what you want based on the captions. Hashtag give Hupo SD3. I agree with that. We really need a Sora level. Okay. What else? Let me see if there's anything else that I wanted to show here. So we talked about the experiment. I think most of this is good. We talked about the recaptioning. We talked about the dimensionality of the autoencoder. Here, they have a bunch of great pictures here. So this is like, we're right there. You know, I was saying that at the beginning of the stream, but it feels like we're right here. You know, I don't really know. These all seem the same to me at this point. You know, it's like we're kind of getting to this point where all of them are kind of the same quality. You know, is there anything wrong with this? Like, not really. This, to me, that's kind of, it's perfect. You can't really make it any better. At some point, it starts to become subjective rather than quantitative. Maybe here the aisle is a little bit too wide. There's a kind of like a weird discontinuity between the shelves there. There's still like little things you can nitpick, but we're getting very close. Here's different model architecture. So they try MMDIT. They compare it to a couple different ones here. The original DIT, cross DIT, and then a UVIT. This is kind of more of a UNet type of architecture. So the MMDIT kind of outperforms all of them on validation loss FID score. QK normalization, this is like a trick that they do. So they pre-train all their models on low resolution, 256 by 256, and then fine-tune on higher resolution, which is pretty standard. We saw that in the previous paper that they did. The mixed aspect ratios. When moving to high resolution, mixed precision training can become unstable and the loss diverges. So mixed precision training is the precision here that they're referring to is the precision at which you're storing the numbers, right? So numbers like the actual gradient, the values of the model parameters, the EMA weights, right? The exponential moving average, like all of those are fundamentally a number that is being stored on a computer, right? And your computer has everything in ones and zeros or bits, right? And you can choose to store things in a lot of those ones and zeros, which would be high precision, or you can choose to store it in a very small amount of ones and zeros, which would be low precision. So obviously, the smaller your precision, the faster you can train, the bigger the model can be, right? Because it'll fit on a less smaller amount of memory if it's at a lower precision. So people now are getting quite fancy about doing not just, okay, let's just train everything with a float 32, which would be kind of the most naive. Right now they have these much more fancy mixed precision type training. And when you're doing this mixed precision type training, apparently there's normalizing the Q and K before the attention operation, prevents the attention logic growth instability, which enables efficient training at BF16. This is the brain float 16 mixed, which is mixed precision brain float 16 type training. But they do say at the end of this, although this method can generally help to stabilize the training of large models, it is not a universal recipe and you may need to be adapted depending on the exact training setup. So this might not actually be the end all be all, right? It could be the situation where you have a slightly different setup, you have a different diffusion model architecture, you have a different data set, you're training on different GPUs, you're training using different learning rates, different schedules. There's like a million different variables that could be different here. So you don't necessarily need to do this. This is just one trick that they found in their particular case to help. Okay. Positional encodings for varying aspect ratios. This was interesting. They use 2D frequency embeddings and have to adapt them based on the resolution. So they're training with a mix of different resolutions. So you can see here, this is a resolution for a cell phone, resolution for a desktop, right? You have wide images versus tall images. Previous generations of Stable Diffusion were largely trained on basically this square. So you crop everything so that it's a square, but then you can only generate squares. So people want to be able to generate different aspect ratios. So they train on different aspect ratios, but in order to train on different aspect ratios, you have to make sure that these positional embeddings, which are representing where you are in the image, are kind of consistent and independent of the aspect ratio, and that's why they have to adapt them here using interpolation. They use a combination of extended and interpolated position grids, which are subsequently frequency embedded. We have a stream on long rope if you're interested on position embeddings. That one kind of goes deep. I'm of the opinion that position embeddings are a little bit overly engineered at this point, and they seem super arbitrary, but what you can do. We use bucketed sampling such that each batch consists of images of a homogeneous size. So they're dividing that. That's how they get the low resolution. This was kind of a weird thing here. So resolution-dependent shifting of time step schedules. So it turns out that depending on the size of the image, the time step schedule, which is basically like, you could think of it like kind of the way that you're picking these time steps here, you want a different shifting factor. So they introduced this like weird shifting factor here. Where is it? Shift value alpha. So depending on the size of the resolution of the image, you're going to pick a different value for this shift thing. And they pick it based on the preference. So they try a couple different shift values. So here's the different shift values. They try a shift value of 3, 6, 2, 4, 1.5, and 1. And ELO score the higher the better. So this is preference across. So this is humans. So humans sit there and they look at different images with different shift values, and then they just run that enough times with enough humans, and eventually they're like, a shift value of 3 is the best. And you can ask them, why is the shift value of 3 the best? And they're like, I don't fucking know, because we asked 100 people and they decided that their little monkey brain just like consumed these 2 images and decided that this one is better than this one, right? So that's kind of where we're at, right? So it's weird because when I look at these, I come to the same conclusion, but it's like hard to say why, right? So like, which picture of these is better? Is this car or this car? This one's better, right? But why is it better? I don't know. It's just better, right? What's a better temple? This one or this one? Well, this one, right? So it's almost like I agree with the human raters in every single one of these instances, but human brains are such a black box that even though I can tell you, for some of these I can tell you, okay, well, this one just looks bad, but some of these it's like, it's very difficult to like explain in words why this is better than this and this is better than this, but it's just like, I 100% agree. So we're starting to like move into a world where some of these hyperparameter decisions are based on subjective human preference ratings that are based on some kind of weird intuition that's very difficult to describe, which is kind of trippy to think about, right? Where think about a future where you're sitting there in a VR headset and you're just scrolling through like a TikTok, and you focus on certain parts of the TikTok, or you focus on certain things more than other things, and then how much you care and focus on certain things is then fed all the way back to some training pipeline in some data center, and changes and adjusts the value of some random thing like this shifted sample alpha, and it changes. And the weird thing about that future is that no single human will be able to tell you why this particular value for shift alpha or this particular value for shift alpha is better. It's just the result of this giant distributed preference coming from huge amounts of humans that are all just staring at pictures. I don't know if that sounds dystopian or utopian to you guys, but either way, I think it's pretty cool. Here's the human preference evaluation. So this is kind of the proof of state of the art, right? So if you're going to claim state of the art, you got to prove it, and this is the proof. Here they did win rate, so the A/B comparison, and this is pretty much all the big ones. They have DALL-E 3, they have Midjourney version 6, they have SDXL, and you can see that SDXL and then SD3. Where's SD3? Oh, this is win rate versus state of the art. So if you're above this red dotted line, that means you're above 50% win rate, which means that you're beating MJV6. So MJV6, look at that. SD Stable Diffusion 3 beats Midjourney V6. Path length. Evaluating human preference. Okay, there was another thing here that I wanted to go into. So let me sip more coffee, see if you guys have any more questions, and then we'll talk about these text encoders. Yeah, Majetti, you're correct that artists would probably be able to describe why. And some people say artists are fucked because, generative AI is like basically doing what they're doing, but I don't think of it like that. The way that I think about it is that artists have a much deeper and structured understanding of like image quality and any type of editing that you would need to do, right? So someone who has a PhD in art, I don't even know if that's something you could get, but they're going to be able to directly describe this, right? They're going to be able to say, oh yeah, the blah, blah, blah lighting and the 3/4 pose here should be a full frontal pose. Like they have the vocabulary, they have this acquired taste and this more complicated visual palette that allows them to much more easily describe and, in that case, prompt exactly what they're looking for visually, right? Which I think is the same case with language models. I think people who have like an English, or not just English, but like a literature background, they're going to be much better at judging text and much better at creating the right prompt to generate text. So I don't think artists are done. I think if you're an artist, you don't need to feel defeated. Like, don't feel like your job is over. Instead, be like, okay, now I got a whole set of new tools, and I'm going to generate better images than the other people, not because they have worse tools than I do, or not because I have the mechanical ability to draw and they don't have the mechanical ability to draw. I'm going to generate better images than they do because I have a much better understanding of images and image quality and stuff like that. So I don't know. I don't think artists are dead. I think they just need to realize that what they really have, what really makes them special, is that understanding and not necessarily the mechanical ability to draw. Okay. Let's talk about text encoders. So if we scroll to this figure 2 here, the model architecture, we see at the very top here that the caption, or what you type into the prompt, is being fed into the 3 separate text encoders, right? And we know from previous diffusion model papers that the quality of the text encoder is very, very important, right? So if you're using some shit text encoder, the quality is ultimately going to be shit. If you're using a very good text encoder, the quality is going to be pretty good. So the quality of the text encoder is very predictive to the final quality of the image being generated. So another thing we know is that ensembles of models are generally better than a single model, especially if the ensemble of models were trained with slightly different objectives on slightly different data sets, right? We know that if you have clip features and you have dino features and you have the features that come out of the segment anything model, those 3 features are going to represent slightly different things about the image, and the combination of those 3 is better than each individual one. The only reason that you don't want to use ensembles of models versus a single model is that an ensemble of models is more expensive to compute and requires more memory, right? So if you were to use all 3 of these models, you need to load clip G14 onto your GPU and then feed the text into that clip G14, and then you're going to get a little vector out. And then you're going to have to load clip L14 into your GPU and then feed your text into that, and then you're going to get a little vector. And then you're going to have to feed T5 XXL into your GPU, and then you're going to have to feed the text into that, and you're going to get a little vector. So that's way more steps and way more memory than just using a single one of these, right? So model ensembles, they work better every time. It's just the problem is that they just take more memory and more compute. So what are they going to do? Well, in this paper, they obviously, to get the best possible results, they're going to use this ensemble of all 3 text encoders, but they do something interesting here where they actually look at what the difference is between these. And where is I? Here. Let me close this. With the main motivation using multiple text encoders is boosting the overall model performance, right? So they want to get state of the art, so they want the best possible text encoding. The best possible text encoding is going to be better if you have multiple models or this ensemble of models. So we're going to train our model with 3 text encoders with an individual dropout rate of 46%. So the dropout rate basically means that as they're training, sometimes they're actually going to drop out what's coming out of one of the text encoders. So rather than actually using what's coming out of the T5 text encoder, they're just going to replace that with a bunch of zeros, right? So that's, you can drop out individual neurons, which is where dropout is usually used. But here they're dropping out entire model or entire encoders when they're training. And that's a very aggressive dropout rate, by the way. At inference, that means you can use an arbitrary subset of all 3 encoders. So this is very clever, right? So because you're arbitrarily dropping out some of these texts, when you're training, sometimes what's coming out of here is a bunch of zeros, or what's coming out of here is a bunch of zeros, or what's coming out of here is a bunch of zeros. So by doing that, you've made your model robust to all of these, right? So your model doesn't necessarily care if one of these isn't even evaluated, which means that whenever you're performing inference, if you don't have a huge GPU and you can't fit the T5 XXL on your GPU, that's totally fine, dog. Just use this clip G14 and it'll still work. If you don't have the model weights for clip G14, but you have the model weights for T5XL, that's totally fine, dog. You can just zero these out and just use that T5XL. So they've made it robust to any permutation of the text encoders that exist there, which is very clever. This offer means for training off model performance for improved memory efficiency, which is particularly relevant for the 4.7 billion parameters of T5XL, which is this text encoder that Google trained, that requires significant amounts of VRAM. We observe limited performance drops when using only the 2 clip-based text encoders and replacing the T5 embeddings by 0, or dropping out the T5. We provide a qualitative visualization in Figure 9. However, one thing that they do find is that removing the T5 has no effect on aesthetic quality ratings and only a small impact on probability errors, whereas its contribution to the capabilities of generating written text is more significant. So I thought this was a really, really cool result, is that when they drop out the T5 text encoder, so basically when they take this here and they remove that, so they just replace this with a bunch of zeros, which is great because it means that you don't need to have a huge GPU. You don't need to load this into your memory. You can just have these 2 in your memory and that's it. But when they do that, the model gets worse at spelling. And it's like, whoa, right? So look at that. Here's a monkey holding a sign, reading scaling transformer models is awesome. If you use all 3 text encoders, right, the full ensemble, no dropout, it's perfect. The spelling is perfect. If you get rid of this T5 text encoder, it now makes mistakes. You see here, transformer, it misspells transformer. It misspells transformer. It says transformer. So that's pretty cool, right? That you can literally see here in this example how that specific text encoder, the T5, is adding this capability of spelling correctly, which makes sense, right? Because these 2 encoders here, the clip text encoder and the clip text encoder here, both of these are clip text encoder, those come out of a contrastive learning process. And that contrastive learning process is about making images and text share the same point in embedding space. So these clip text encoders are very good at taking kind of the semantic knowledge of an image and a text, right? So they're very good at like it's very difficult to describe because I'm trying to describe something that's like very black boxy and high dimensional, but these are like almost like imagey semantic text encoders versus this T5 is not trained with the same objective. So it's going to be a slightly different kind of type of text encoding that's coming out of that. So it's very similar to the way that you can do ensembles of like the dyno features and the clip features, right? Where the visual features that come out of a dyno versus the clip, they're going to be different, right? Because the way that those were trained is different. And the same thing is happening here where the different text encoders have slightly different strengths and weaknesses so that whenever you use them in combination, that's where you really get the benefit. So here, for example, this picture of the ferret, this is a mischievous ferret with a playful grin squeezes itself into a glass jar. If you have all 3 of the text encoders, the ferret is always in the jar. Versus if you don't have all 3 of the text encoders, it kind of ignores the into part of that text. And the ferret is just kind of like around the jar, but not specifically in the jar, right? So this T5 text encoder is very, very, has a much more nuanced kind of definition about this token here, the into word, where it very specifically wants it to be inside the jar versus the clip encoders. They don't really seem to care that much, right? They're like, oh, ferret, jar. Okay, here's a ferret and a jar. I don't know. I just thought that was kind of cool, but Sam has a point here to add. The T5 is also a better visual question answering model out of the ones I've tried. Maybe that's why it does that better, right? Because if I don't exactly know what T5 was trained on, but if it was trained on some kind of VQA, like visual question answering, maybe there's questions in that data set which are like, is the turtle in the box or is the turtle outside of the box, right? So even just that slight difference in the training data means that T5 text encoder is going to have slightly different representation, which is focusing on slightly different things. I don't know. Pretty cool stuff. Conclusion. We presented a scaling analysis of rectified flow models for text-to-image synthesis. We proposed a novel time-step sampling for rectified flow training that improves over previous diffusion model training formulations and retains the favorable properties of rectified flows. We also demonstrated the advantages of our new transformer-based MMDIT architecture. Finally, we performed a scaling study and compare model sizes up to 8 billion parameters and 5 times 10 to the 22nd training flops. We showed that validation loss improvements correlate with both existing text-to-image benchmarks as well as human preference evaluations. In combination with our improvements in generative modeling and scalable multimodal architectures, we achieved performance that is competitive with state-of-the-art proprietary models. I don't know, they are state-of-the-art. I feel like the figure here kind of proves it for me. I don't feel like they need to shy away from that. You did the human result. You know, you did it. You got a bunch of humans, and pretty much they universally agree that SD3 is better. So I don't know, you can proudly claim that. You don't have to say is competitive. You could just say is state of the art. The scaling trend shows no sign of saturation, which means that we can optimistically continue to improve performance. And that's pretty much it, guys. Let's see, is there anything else interesting here? Oh, they do train it with direct preference optimization. This was kind of an interesting little thing here. It's like kind of like a throwaway line. I think it's over here. Yeah, right here. We align the model using direct preference optimization as described in Appendix C. So it's a 3-stage pipeline. So they do pre-training at a small image resolution. Then they fine-tune at a larger image resolution. And then they do DPO, which you could think of it kind of like a PPO. It's kind of like a, I don't want to say RLHF because that has a whole series of connotations, but it's basically that, right? So in RLHF or PPO or DPO, you're basically saying, okay, this is my model and it's generating these things, but here is a data set of good examples of generations, right? And that's how you can take a model that just generates, just auto-completes, usually just called the pre-trained or raw model, and turn it into this kind of instruction tune model that can answer these conversations. Except in this case, it's not like they're doing DPO or PPO or RLHF so that it does this kind of back and forth conversation style. They're doing DPO on a specific data set. So if we go to Appendix C, there's 128 captions from the party prompts set. So they're doing DPO to as the third final stage of this training pipeline, right, where they have the pre-training, then fine-tuning, and then DPO to basically make it more visually pleasing, right? So we introduce, and they don't even push gradients for the whole model. They basically have these LoRa's, which are little tiny additional matrices that you can then merge into the weight, into the model. But they push gradients into those LoRa's from this party prompt set, and that's probably how you get the more kind of like aesthetically pleasing, right? So one way to think about why they would do this is that we're at the point of image generation technology that you're using these human preference studies to determine which model is better. And humans, right, we watch movies and we're very used to kind of visual content. So we prefer content that is like visually pleasing, right? So even though the diffusion model, what it wants to do is generate images that are as close as possible to this data set, this CC12M, that's not going to give you necessarily the highest possible score if you're using a bunch of humans that are being told which image do you like better, which image is more aesthetically pleasing. So they're doing this additional DPO step so that they basically, I don't exactly know what party prompts is, but I bet you it's like captions and then very aesthetically pleasing, like cinematic looking things, so that the model, rather than generating just images that look like you were pulled from this CC12M, it'll generate images that are more aesthetic, So like when you look at these look more aesthetic, right? This looks like something that you would see in like a movie. So I don't know. I thought that was kind of interesting. The idea of like DPO for like aesthetic reasons, which is technically moving you away from the true distribution, right? Like fundamentally, the way that diffusion models are being trained is that they're trying to match this data distribution P0. And this data distribution P0 is supposed to represent all possible images of the real world, right? But you don't actually want to match that distribution exactly. What you really want to match is the distribution of aesthetic images that are paired with relatively simple captions, right? Because you also want to make sure that whenever people are using this, they're not going to make really fancy captions, right? They're going to have weird, shitty captions because they're just sitting there and they just type in like 4 words. So you want to just do a little bit of preference optimization for shitty caption, visually aesthetic, pleasing image, so that the model will generate visually aesthetic, pleasing images so that you can get a high score using human evaluation studies so that you can claim state-of-the-art. Preference optimization technique. Yeah, that's a better way of describing it. Okay. You can do editing. I thought this was kind of cool. Go big or go UNet. So change is written on the blackboard. So you take this image, do a little masked editing here. Make a sign that says MMDIT rules. To be edit model. They also do some deduplication. So they go through their entire data set and they deduplicate. So they basically take all the images, embed them, and then use the FAISS, the Facebook. This is what people use for like RAG, right? Similarity search, where you're basically comparing the embedding of different texts, except here you're comparing the embedding of images. So if there's multiple images that are way too close, the embedding of both of those images is just really, really similar. It probably means it's a duplicate image. So if it's a duplicate image, you don't want to train on duplicated data because then you're just kind of like, right? Imagine if you have the same picture of a pig 50 times. So whenever you're going to train this model, you're saying, here's a picture of a pig, and it's the same picture of the pig, and here's the same picture of the pig, and here's the same picture of the pig. So you're kind of like overfitting on that specific picture of a pig so that whenever you generate images of a pig, it's going to look a lot like that one specific picture of a pig because it's seen it like 100 times compared to the other ones that it might have only seen 10 times. So deduplicating is important so that it captures a nice variety of visual concepts rather than kind of overfitting to whatever the most common common image for a specific concept is. Okay, I think that's pretty much it. Let me see if there's anything else I had here. Rectified flow, vector field, autoencoders, CC12M, transformer. Okay, that's pretty much it. We're at 11:49. All right, I'm going to pause, drink some coffee. You guys ask some questions, and then we will summarize the stream. Okay, no questions. All right, so today we reviewed Stable Diffusion 3. Stable Diffusion 3 is the latest version of Stability AI's image generation models. Stability AI is a startup that creates open source models, and they published this paper, which is called Scaling Rectified Flow Transformers for High Resolution Image Synthesis, which is the result of a bunch of people's work. So you can see here there's like, whatever this is, like a dozen people. And this paper is the combination of all the work that those dozen people did. So it's a bunch of different tricks and improvements and optimizations. And it's a great paper. I really like this paper. I think it's a really good summary of all the different types of diffusion models that people have tried. And I really appreciate Stability for giving us this. You know, I would love to have this paper, but for OpenAI. I would love to have this paper for Midjourney, you know, because Midjourney and OpenAI, they have teams similar to this team that are running these type of experiments and doing these type of analyses, except that whenever they discover things, they don't tell you about them. And I think that's really sad. You know, I think that you want to share, and I really appreciate that these guys are sharing. So there's a bunch of different things that they do in this paper. And one of the first things that we were looking at is this idea of flows. So a diffusion model is fundamentally flowing from a noise distribution to a data distribution, where the data distribution is the distribution of images, specifically CC12M combined with ImageNet, and then probably some other mix of data that they put in there. And this flow, the way that it usually works now, it's not very straight, so it's curved, right? And what it means by that is that the path you're taking over a series of steps, right? One inference step, another inference step, another inference step. It's not very efficient. You're kind of like meandering around until you finally get to your point, which you want to get to, which is your sample from your data distribution, right? And I think this picture kind of shows it the best, right? This top row here, where ultimately what you want is this. You want the picture of the cat, but if you think about just the dimension of the color of the cat, right? You're going from a brown cat to an orange cat to a white cat to then a gray cat to then a slightly darker gray cat to then the actual gray that you want, right? So the path that you took there isn't very straight, and it would be better if you took a much straighter path, right? So that's kind of what rectified flow is trying to do, right? Rect, you could think like a rectangle, like a straight line, right? So rectified flow is, let's just take a much straighter path to do that. Here they go through, they kind of talk about, they basically present the problem of diffusion models in such a way that you can formalize this loss function or this objective here, and then show that all the different variants of different ways of doing this that people have come up with are basically this, but just you're substituting this term here. So people have tried EDM, rectified flow, cosine, and LDM, and they're going to try all of those. Rectified flow is the simplest one, where you're literally going from your image distribution to your noise distribution, and the path to that is completely straight. So you see here 1 minus t, and then t, that's a completely straight line from your noise at time step 1, and then your image at time step 0. So it's like a straight line, which is great because that's really easy compared to some of these other ones that are a little bit more complicated. Another thing they look in here is the specific way that you sample where in the time you're going to be training on, right? So whenever you're training and you're pushing gradients into these diffusion models, you're picking some specific time step, right? So you're going to be picking some random time. You're going to pick an image, and then you're going to pick some random time step, and then you're going to add a little bit of noise and then push a gradient based on that. So where do you pick the time step, right? Do you pick this one here? Do you pick this one here? Do you pick this one here? So you could pick any one of those, and most papers, what they're doing is they're just assuming a uniform distribution. So they're saying, okay, over the course of training, I'm basically going to pick a random time step anywhere from 0 to 1 with equal probability. In this paper, they introduced this new distribution for picking the right value of t, and they call this log-it normal sampling, which comes from this log-it normal distribution. And kind of the long story short is that you're mostly going to be picking time steps in the middle. And the intuition is that in the middle here, this is where really that's where you're really going to build a good understanding of this data distribution, right? Because from here to here, you're going from noise to like slightly less noise, or going from almost a cat to a cat is not, neither of these is as difficult as this one here, right? This is where the real crux of this process is. So they decide to bias the time step sampling to specifically the middle part of that. And there's a couple other variants of that people have tried. So for example here, mode sampling with heavy tails and cosine mapping. Both of those, so whether it's the specific type of flow or the specific type of sampler, they ablate all of those. So they try every one of those combinations. So there's 24 combinations in total, and they basically score them using CLIP and FID, which are these metrics that basically are telling you how well captions match to text, or captions match to images, and how close the images are together, right? These are distance metrics. And what they discover is that this specific combination of rectified flow plus this log norm is basically the best variant of the specific formulation of a diffusion model problem that you want to be picking. So very convenient, and I'm very glad that they put this out there, because by putting this out there, it means that you no longer have to perform this experiment. So if you were going to make a startup that was going to do generative images, if Stable Diffusion did not release this, if Stability AI did not release this, you would have to perform this experiment. But now, because they have released this and they've done the experiment for you, you can just go directly and start using this specific form yourself. So you're saving people a bunch of compute by publishing the results for this. And that compute correlates to GPUs that are burning and causing climate change. So if you really care about climate change, you would publish your results so that other people don't have to perform the experiment for you. So all these people that say that they care about climate change, and they don't really care. They care about money more than they care about climate change, because they're going to let you perform this experiment and you burn $5 million worth of GPUs in order to come to the same conclusion that they came to a year ago. How about that? Okay, so that's one experiment that they run. Another thing that they show in this paper, or another result, is they have a new architecture. So these diffusion models, there's different parts, right? You have your encoder, but the meat of the diffusion model is this diffusion, the one that actually does this noise prediction, right? So this thing here, this noise prediction objective, this little model parameterized by theta that basically predicts the noise so that you can remove it. That you're using architecture for that. Normally people use these UNets, but now people are using these diffusion transformers, this DIT, and they try a couple different diffusion transformers. So they try, let me see right here, they try DIT, cross DIT, UVIT, and MMDIT. So the one that ends up working the best is MMDIT. MMDIT is this here. It's basically your standard transformer block, except they do this clever little trick here where they separate out the visual features and the text features. So the text features and the visual features each have their own little separate MLP here, right? So in a standard transformer, you don't have that. In a standard transformer, you're doing a cross attention between the image and the text features. But in this one, they concatenate the text features and the image features, and then do a self-attention between the concatenated text and image and the concatenated text and image. So it's a little bit more computationally complex, right? The size of that square, of that attention square, is bigger because the sequence length is now bigger, because you're basically concatenating these sequences, but it allows more information to flow between the different modalities, right? Because both representations can work in their own space, yet take into account each other one. So a nice little, little architecture. I don't know if they might not have necessarily come up with this trick. I'm sure there might be some paper that they reference here from like fucking like 2021 or something that they like use, but okay. Great little trick. Model architecture. And then what's the next thing? They show some scaling stuff. So obviously the bigger your autoencoder, specifically the dimensionality of the feature or the channel dimension of your autoencoder, the bigger you make that, the better it is. Also, the deeper you make the model, so the more transformer blocks, the better it is. The wider it is, so the bigger this hidden size is, that's like kind of the width, the better it is. And the more the number of attention heads, the better it is. So there's a bunch of different parts of this which largely determine the size of the model, and the bigger you make any one of those dimensions, the better the model performs. So this is kind of the scaling law that they're saying. They're saying, hey, it doesn't seem to be like a situation where there's a magic like size that works better than the other ones. It seems that as you keep increasing these things, they're just going to keep getting better and better, which is great, because it means that a year from now, with the bigger GPUs that we're going to have, we're just going to make this D bigger, and then it's just going to perform better. They train on CC12M and ImageNet. They do some filtering. They also deduplicate, and then they also do the kind of caption augmentation that we've seen before. In this case, they're going to be using an open source vision language model, CogVLM, to augment these captions. And that's pretty much it. There's a couple other tricks here. The QK normalization, pre-computing image and text embeddings. This was another little trick. So rather than whenever you sample data for your mini batch, if you just sample images in image space and you sample text in text space, you have to basically encode them using these encoders before you can actually feed it into your model and push the gradient. So in order to speed things up, what you're going to do is you're going to actually, before you do any training, you're going to feed your entire data set, all the captions, you're going to feed it into these 3 text encoders, so that whenever you're doing training and you're sampling for your mini batch, you're just sampling already encoded text, so that you don't have to be encoding text at training time. That's a pretty standard trick that most people use, but I figured it's worth mentioning. What else? Yeah, the one other thing that I think is worth talking about here is the text encoders. So they use an ensemble of text encoders, specifically clip G14, clip L14, and then T5XXL. And these 3 text encoders, which they train with a very high dropout rate to make the model very robust. So you don't need to use all the text encoders at inference time. You can use a subset of the 3 text encoders. If you're trying to run this on a very cheap computer that doesn't have a lot of GPU VRAM, you can just use the smallest text encoder. If you want the best possible performance and you have a huge GPU, then you can use all 3 text encoders. And they do this nice little analysis here where they realize that the T5 text encoder specifically seems to be the one that is the most important for determining the spelling of words, which is, I thought, kind of an interesting little result. And yeah, the scaling trend shows no sign of saturation, which makes us optimistic that we can continue to improve the performance of our models in the future. I don't know, we didn't really look too much at the actual images. I figured most of the other videos on YouTube, like, they don't dive as deep into the math and stuff as we do here, but they do look a lot more at the quality of the stuff. So I don't know, if you guys are more interested in kind of that stuff, maybe check out other videos, but the quality seems pretty good. I think, like, we're very much at the top of the S curve. You really have to nitpick to, like, find errors in these images. They look very aesthetically pleasing, and part of the reason they look aesthetically pleasing is that they're using DPO to basically just give it one little extra tuning so that it gives you these kind of aesthetically pleasing images, even if you have shitty captions. But that's pretty much it, guys. I probably forgot to summarize one thing or another. You know, this paper was very information dense, but in a good way. It's, I think, probably the best diffusion model paper I've read, you know, but I think it's also because it's the condensed work of like 12 different people, which is why it's so dense, you know. But that's it. That's all I got. Tomorrow we are going to be looking at one of the kind of another paper from Stability AI, but in this case it's generating 3D. So this is TripoSR. If you're interested in how you can take 2-dimensional images and turn it into a 3-dimensional object, definitely join us tomorrow. If not, have a great weekend. And thank you, Majetti, Aries, Sam, Beck Pro, Timothy, Sporkamat, Ed, Michael, who else? Roman, Rafael, Aries, 87GN, Black People, that's kind of a weird name, Joseph Enoch, Akdon, The Big Fortuno, Drumil, Beck Pro, 2ARX, Tim Anderson, Meme Poppers, Sagar. Thanks everybody for listening. Hope you got something out of that. Feel free to join the Discord if you want to discuss further, and see you guys tomorrow.